Welcome back to this next video in which we are discussing finitely generated field extensions. Okay, so we're now going to see the final theorem for this video, and it's going to be an extension of the thing that we said right at the end of the previous video. So at the end of the previous video we were able to conclude that the degree of a finitely generated field extension over the initial field, capital F, was going to be finite. What I now want to do is show you that actually it works both ways round. So let's state this theorem nice and formally here. Okay, so the last theorem then. So one last theorem, and I'll underline this one in orange. Okay, right. So this is the theorem then, that K, which is a field extension of F, is going to be a finite field extension. Okay, which means that the degree of k over f is just finite, rather than it being infinite. Okay, so the degree of k over f is finite if and only if, okay, so if and only if k is a finitely generated field extension of f, where the finite number of generators are all algebraic over f. So if and only if, and I'll write k is generated over f, okay, so k is generated over f by a finite collection of generators, which I'll just denote by alpha 1, alpha 2, all the way up to alpha n, which are algebraic over f. Okay, so it's finite if and only if it's generated by a finite number of algebraic generators over f, which are algebraic over f. So quite a long theorem to actually state. Okay, so this is the other statement. So we want to prove that these two statements are utterly equivalent to one another. And we've already done one way round. Okay, we've already done the if. We've already shown that k over f, or k, which is a field extension of f, is going to be finite if k is generated over f by a finite number of elements which are algebraic over f. We've shown that if you do indeed have a finitely generated field extension of f, it will be finite over f. Okay, so that's absolutely fine. Now what we want to do is take on the only if. Okay, and in order to show the only if, what we actually need to show is that if k over f is finite, then it implies that k is generated by a finite number of elements which are algebraic over f. Okay, that's what we need to show, because if we show that if this is true, this is true, then the only way this can be true is if this is true. Okay, because if this wasn't true, then this couldn't be true, because if it was true, it would imply that this was true, which is a contradiction. Okay, so this arrow is the equivalent thing to proving the only if here. Okay, and it's a little bit of a skill in itself, understanding that the only if means this arrow means that we need to show that this implies this. Okay, the if you like, is showing that if this is true, this is true. Okay, which we've already done. The only if is the other opposite way round arrow there. Okay, right, so what I want to do then is start off with the assumption that k over f is finite, and then arrive at the fact that k is generated over f by a finite number of elements which are algebraic over f. Now this is extremely easy. Okay, so what we know is that the degree of k over f is equal to some finite number, n. That's where we're starting off with. We're starting off with the assumption that k is a finite field extension of f. Okay, now what I want to do is find you some algebraic elements, so elements that are algebraic over f, okay, which are all, which will generate k if we use them as generators for a field extension of f. Okay, now the first thing to say is that all the elements of k are actually going to be algebraic over f. Okay, and the reason is that in the video on algebraic field extensions, we showed that if you have a finite field extension of the field f, then you can instantly conclude that that finite field extension is an algebraic field extension. Okay, so that's a proof that we did in the video on algebraic field extensions. Okay, so we now know that k is going to be an algebraic field extension of f. Okay, algebraic over f. Now that means that all of the elements of K are going to be algebraic over f. So all I actually need to show is that K is generated by a finite number of elements over f. Okay, because I instantly know that all the elements in K are algebraic over f from the fact that K over f is finite. Okay, right. How can I find some elements then that I can use to generate a field extension of f that is actually equal to K? Well, I can use the basis vectors. Okay, if K viewed as a vector space over f has dimension n, then that means that I can find a basis for K over f which has n basis vectors in, so let's call them v1, v2, all the way up to vn. Now I claim that I can use these to generate K as a field extension of f. So I claim that if I look at the field extension of f generated by v1, v2, all the way up to vn, that this will actually be equal to K. Now why can I claim that? Well, from my new understanding of finitely generated field extensions, where the elements are algebraic over f, which I know they are going to be because all elements in K are algebraic over f, okay, I can say that to build this thing, I just need to look at all polynomials in n variables evaluated at v1, v2, all the way up to vn, and the coefficients of those polynomials are going to be in the field capital F. Okay, in particular, some of the polynomials that I will have to look at will be things of the form a1 times v1 plus a2 times v2 plus all the way up to an vn, these sort of polynomials, okay, where the ai's here are elements of the field capital F. That is certainly a polynomial, okay, it's just the polynomial where I just have the monomials x1, x2, all the way up to xn here, and then they've got coefficients in front of them, and then added together. Okay, now of course if I evaluate that at v1, v2, all the way up to vn, I'll get something of this form. But I know that all the elements of the larger field extension K can be written in this form because these are a basis, an F basis, okay, a basis over the field F for the field extension capital K. Okay, so that means that these polynomials, when evaluated at v1, and I'll just write out the actual polynomial. The polynomial will be a1, x1 plus a2, x2 plus all the way up to an, xn. Okay, these polynomials here, when evaluated at v1, v2, all the way up to vn, will give me every possible element in the field capital K, because I will actually get all these linear combinations that have to span the entire field extension capital K. Okay, so yes, I'll have all the other polynomials as well, the much more complicated polynomials, but I know that they will all just be equal to elements of this form, okay, in some complicated way that I don't need to understand. Okay, they will be equal to these things because these things do indeed span the entire field extension K. Okay, so that's why I know that when I generate the smallest field containing v1, v2, all the way up to vn, the basis vectors for K as a vector space over F, I will actually get all of K, because just look at these polynomials. Don't worry about all the other polynomials. Yes, that they are horrendously complicated, but you know that when you evaluate them at v1, v2, all the way up to vn, you must just get something back in K, and everything in K is covered just by these polynomials, so they must be equivalent to one of these polynomials. There's no other way. Okay, so you don't need to worry about the other horrendously complicated ones. You've got all of K just with these simple polynomials, and that's how you can conclude that this is all of K. You don't need to worry about the higher polynomials. Okay, they have to be in K, that they can't be anywhere else. Okay, right. There then is the proof that indeed K is going to be finitely generated by these elements, these basis vectors, v1, v2, all the way up to vn. So now we know, therefore, that if the degree of K over F is finite, if K is a finite field extension of F, you can conclude that there is a finite number of elements in K that are algebraic over F, which will generate K as a field extension of F. Okay, and with that we will end this video on finitely generated field extensions.